Welcome back to MOVI-C Control Cabinet Products Basic to Intermediate Training. This is Session 10, which happens to be Lab 3. We're going to learn to control the MOVI drive technology in what is called terminal control mode, also known as binary mode. This is probably one of the simplest ways to control a VFD. You don't need to have any kind of field bus connection. You don't have to have a programmable logic controller or digital controller of any kind. You can just control the drive with a few switches and you can get feedback with a few lights. It's a very simple mode. What's nice is you can adapt terminal control mode to operate with a PLC or digital controller just by manipulating the digital inputs and reading the digital outputs on the VFD. But you don't have to. That's the big point. So this is probably the simplest way to run your VFD, and you can use this for real applications. So we're going to dive into this and learn a bit about terminal control mode. A very quick word about motors for this particular lab. If possible, use an asynchronous motor for this lab too. If you used it for the last one, then just continue right on. Everything's good. It is possible, however, to use a servo motor, but the lab procedures again are different, so there are two sets of instructions linked in the description section. Download the one that matches your motor and you'll be just fine. Again, I'll be following the instructions for the asynchronous motor because that's really what we designed this lab around. We have a few pre-lab instructions. I'd like to explain some of the concepts behind terminal control mode if this is a new topic to you, so let's take a few minutes to discuss that. Now, the first thing we need to talk about in order to understand terminal control mode is digital logic. We're going to be controlling the VFD using its digital inputs and outputs. We need to understand how digital logic works. Digital logic is based on the concept that there are just two possible conditions that a signal can be in: high and low, on and off, 1 and 0, true and false, and you could probably add yes and no. There are only two possibilities here. That's why we call this binary control mode, because we're dealing with just two possibilities. So the system is going to be dealing with the inputs being either high or low and making decisions based upon them. The system will signal output information by turning digital outputs to high or low conditions, sending a signal out. Now, in most digital control systems, high and low are represented by two voltage levels. You can represent high and low in other ways, for example, by two current magnitudes, but that's less common. Voltage is very popular. In most industrial control systems, low equals 0 volts DC, and high equals 24 volts DC. So that's a really simple system. 24 volts is used in industry because it's a fairly large DC voltage, and that tends to prevent noise from becoming a problem on the lines and causing false signaling. This is the one that you'll often see with digital controllers and PLCs. Now, with MOVI drive technology and other similar VFDs that SCW puts out, we define low as nominally 0 volts DC, but actually you can go anywhere between -3 and +5 volts DC and have it considered a low. There's a window, in other words, where the voltage can be, and as long as it's within the window, the signal is interpreted as low. A high signal is considered nominally 24 volts DC, but the official window is +13 to +30 volts DC. If your voltage falls somewhere within that space, it will be interpreted as high. So really simple. Digital logic is easy to understand. It's one reason a lot of people like it. I'll just mention as a brief aside that there is another system found in some places. You will encounter it with some PLCs. It is called TTL, which stands for transistor logic. It's a 5-volt system. So it uses 0 and 5 volts to signal low and high instead. It's not as popular in industry because it's more susceptible to noise. With a lower voltage like this, if electrical interference gets imposed on the line by induction, it can easily fall into that 5-volt range and create spurious signals. 24 volts is a little more immune to noise because the voltage is higher, but you should be aware of both systems. Now, as I said just a few minutes ago, terminal control mode is often called binary control mode, and that's because it's using binary signals, highs and lows, to control devices like VFDs. Let's talk about how binary control is typically implemented. So for example, here's our MOVI drive technology. Remember, it has 8 built-in digital inputs and 4 digital outputs, plus a relay contact. Well, what we can do is we can connect sensors that output highs and lows to the digital inputs. As long as they have compatible voltages, we can work with them. For example, this prox sensor detects the presence or absence of an object passing near it, and it outputs a high or a low to indicate whether that object is present or absent. If we connect that up to our VFD, it will monitor that signal and it can make decisions based on it. We can connect the digital outputs to a compatible indicator, for example, to lights. Lights are frequently used in industry to signal things. There are all kinds of indicators. Again, if they're compatible with 24-volt logic, you can usually interface them to a MOVI drive technology's digital output. And then there are switches, like, for example, the control box on our demo unit, and of course, all kinds of other switches. As long as these are wired up correctly to a 24-volt power supply, they too can communicate with the digital inputs and trigger all sorts of things. Modes of operation, speed set points, acceleration ramps, direction. They can signal errors and faults. They can be used to reset a fault on the VFD. There are just so many things you can do with switches in industrial control. So these are one of the prime things we connect up to digital inputs. And of course, we're using our control box on our demo unit, which also includes some lights, as our main interface. So we'll be using that when we do the actual lab. If you really want to get sophisticated and interface a terminal control application to a PLC, you don't have to do anything fancy like hook up a field bus. You can just wire the PLC's I/O system directly to the digital inputs and outputs. So terminal control mode is sometimes actually used in a very sophisticated way by interfacing to a PLC. Never forget that that opportunity is available to you. Just remember, whatever you do, be sure that you have 24-volt compatible logic, and as long as that's true, everything should talk and play nicely. Now, the mode that we're going to explore in terminal control mode allows us to run the VFD in speed control mode, and we can have 6 different speeds. We call these speed set points. They are programmed as parameters through MOVI-C. You can see the list here. I've just arbitrarily set up some speeds, and these are accessed by number. So you use 3 digital inputs to create a binary number between 1 and 6, and that picks the speed set point that you want the VFD to operate at. Notice that we start our numbering with 1, which in binary is 001, and we end with 6, which is 110, so it's not 0 through 5, which is what you might expect. It is, in fact, 1 through 6. If you pick speed 0, nothing will happen. There is no speed 0. And if you pick speed 7, which is also possible with 3 binary inputs, nothing will happen either. All right, pretty simple. And you can do a lot with 6 speeds, so SEW considered that sufficient for many applications. The last thing we need to talk about before we jump into the lab itself is what's called active levels. Active level simply means the logic level, in other words, high or low, indicating that the device has been activated. So for example, if we connect something up to a digital input on our VFD and we say it is an active low device, what that means is that if it's outputting a 0, a low, it means that it's been activated. Now that may seem backwards to us. We probably more often would associate high with being activated, but there's actually no rule to indicate high has to always be the activated state. In active low, it's not. A 1 means nothing's happening on the input device that's connected up to our VFD. On the other hand, active high is kind of the opposite. If your input device is active high and it's connected up to a digital input, if it's outputting a low or a 0, it means it hasn't been activated. And if it's outputting a 1, it means it has. Perhaps you're wondering now, why do we have active high and active low? Shouldn't we just have one kind of input device and probably active high because that's more intuitive? Well, let me explain this by showing 2 illustrations. Let us say you have a fault sensor connected up to your VFD. It's going to detect some kind of fault, like maybe a jam or something. The fault sensor is probably going to be active low, meaning that if it outputs a 0, it indicates it's faulted, something is wrong. And if it outputs a 1, it means nothing's wrong, everything's good. You may think, why do we do that? Well, think about this. Fault sensors are important. If something goes wrong, you definitely want to know it, and it's better to be safe than sorry. So, what happens if the wire gets cut, the fault sensor malfunctions, its power supply fails? What's it going to output? Probably a low, and that will trip the fault. Now, maybe that wasn't a real fault, but as I said, it's better to be safe than sorry. So most critical sensors are active low as a kind of safety feature, meaning if the wire gets cut or their power supply fails, they'll trip the fault and shut things down usually. There's a technical term for this. It's called fail-safe. And what it means is that if a device fails, it will fail in the safest possible state. By the way, we often indicate something is active low on a schematic or in our engineering software by putting a slash in front of the signal name. In some schematics, they put a bar over the top of the signal name. It means exactly the same thing. It means it's active low. Now, let's look at an active high device, like a start switch. This is just a button maybe that you push to start a process. Start switches are typically active high, so if you're not touching the switch, it's outputting a 0, and if you press it, it's outputting a 1. Start switches and other similar controls can be active high because they're not mission critical. If the wire gets cut, all that happens is the start switch doesn't work. It doesn't actually create any kind of danger. And so frequently they are active high just because it is a little more intuitive. Actually, though, if you stop and think about it, there is even a safety aspect to this start switch being active high. If it were active low and the wire got cut or some malfunction happened, it could actually start up the machine unexpectedly, which would be undesirable. So choosing between active high and active low can be a safety decision where you pick the state that will cause the machine to behave in the most safe way. Of course, many switches and other control devices don't do critical things. For example, mode switches might not really do anything important, and in that case, it would be your call which you used. Many of those would be active high just because it's a little more intuitive. But do understand that's why active high and active low both exist. Active high devices have signal names without a slash in front of them, so absence of a slash or bar means active high. Nothing too hard about that. Now let's talk about output devices that receive a digital signal into them, and that signal triggers an action of some kind. They too have active levels, and it means exactly the same thing, the logic level that triggers an action in the device. And it's the same rules. Active low, if you send it a 0, a low voltage, that triggers the action. If you send it a 1, it means there's no action. Active high is just the opposite. If you send it a 0, it means don't do anything. If you send it a 1, it means perform whatever you're designed to do. Let's look at an example here. VFDs usually can control electromechanical brakes, so they would use a digital signal to control the brake, and it is usually active low. And it's for exactly the same reason that we had the fault sensor be active low, for safety. What happens with an active low brake? Well, the brake engages when it receives a low signal and releases when you send a high signal. What happens if that wire gets cut? The brake will engage, which is probably a safer action than being released. Notice again the signal name brake has a slash in front of it, indicating that we're dealing with an active low output device. On the other hand, something simple like an indicator light that just shows status is probably active high. That means if the digital output is 0, the light is off, and if it's 1, the light is on. That is very intuitive. Indicator lights are not mission critical. If they don't work, they just don't light up. So we often do make them active high, and we indicate that that signal is active high by the absence of a slash or bar associated with the signal name. All right, that is all I have to say about digital logic. So now we can go ahead and we can pause the video and do the lab. And when you're done, come back and I'll demonstrate it. All right, well, I hope you found that enjoyable and found terminal control interesting. Now let's do our lab walkthrough. Okay, well, we are ready to continue with our next lab, and I'm picking up where I left off, but of course, if you're coming back after being away, you'll need to load your project. This is where we were at the end of our basic startup. We're going to run our drive in what's called terminal control mode today, or binary mode, and you've just spent some time learning about that, so I don't need to say much more about it. So let's just dive in and start making the changes we need to play with our drive using the switches on our control box. The first thing we need to do is change to a mode with some feedback, because we do want to get feedback from our encoder, and we want to use one of the more advanced motor control modes. So the first thing we need to do is go to drivetrain 1 and just change our control algorithm from VF, which is kind of the dumbest control mode, to VFC+. I could have used CFC as well because that also works with asynchronous motors, but VFC Plus is actually an excellent choice for many asynchronous motors. If you have a synchronous motor, you would be using CFC instead. But I've picked VFC Plus and I've already keyed in my encoder, so it knows it's there and it will use it. I'm going to now transfer the drivetrain to the device, and once again it warns me that the drive can start automatically. I've checked that everything's safe and I've got controller inhibit, so I'm confident I can click Activate Startup State. And there we go. I've now switched to a more advanced mode that will in fact take advantage of my encoder and give me better speed control. By the way, if you didn't see the screen I'm on right now, you can pick it just by clicking these boxes here, and these will take you to the screens connected with the motor, the encoder, and the control system. In my case, it defaulted there. All right, so I've taken care of that. Now what we're going to do is configure the access so we can use the jog mode function control block, FCB, to operate the drive. We're going to jog the drive using some switches on our control box, in other words, digital control of jogging. We need to assign 4 of our digital inputs to control that FCB, the one associated with jogging. First thing we need to do is go to the Inputs and Outputs menu, which is part of the function group. And I'm using the built-in I/O, so I pick Basic Unit here. If I have an expansion card, that's what I/O card is for. I pick Basic Unit here, and you can see my digital inputs, DI00, which is always controller inhibit, through DI07. DI01 through DI07 are selectable, and you do it just by popping down these little control boxes and picking different things you want to associate with those. My digital outputs are over here, DO00 through DO03, plus I have my relay, DOR. DB0 is connected to the brake, and that's a permanent assignment. You can't use it for anything else. We're not going to do anything with the digital outputs yet. We'll come back and do something with them later. But the first thing we need to do is we need to associate the jog function control block with 4 digital inputs. We'll use 1, 2, 3, and 4. So according to our instructions, what I need to do first is assign DI01 to FCB20 jog mode. So I need to scroll through this list until I find FCB20 jog mode. This, by the way, is the default selection group. Almost everything you need for the lab is here. If it isn't, you go to extended selection and you'll see an absolutely humongous list. But everything for the lab is in here. And there's FCB20 jog mode. So I pick that and click apply. That assigns it to that first switch. Now I need to use FCB20 jog mode positive and negative for the next 2. So I'm going to look for FCB20 jog mode positive and negative. That's clockwise and counterclockwise. That allows me to pick direction. There's positive and negative is right underneath it. So there we go. That lets me pick direction. And the very last thing I need to pick is speed set point 2. There are actually 2 jog speeds, and this allows me to select between them. That's all I have to do. Now notice I've got a default setting, fault reset on DI05. I'm going to get rid of that by assigning it to no function. And there. Now my other digital inputs don't do anything, so there will be no unexpected behavior. All right, so what's going to happen? When I turn DI01 on, it will activate FCB20 for jog mode. 2 or 3 will select the direction, and 4 will select the speed. Pretty good. However, we haven't configured the FCB yet. We really need to do that, so we're going to go to Drive Functions, the menu here, under Functions, and we're going to find FCB20, jog mode, and we're going to configure it. Now notice we have our 2 drivetrains, but we're only using the first one, so our first column is what we're using. We're going to ignore the others. And according to the instructions, I should set my first jog speed in each direction to 100 RPM and my second to 500. So I'll double click on 200 here. I'll key in 100. Don't forget hit enter or it won't stick. And I'll put 100 for the other one, and then 500 and 500 for the faster jog speed. They give you 2 speeds because often you want a higher speed to go where you're heading and then a lower one to kind of tweak it. So I've done that. I've selected my 2 jog speeds, and my clockwise and counterclockwise directions are the same. You could have different ones, but we don't need to here. All right, so that's not too bad. We're not going to change the acceleration and deceleration. The defaults are fine for this exercise, but you could set those if you wanted to. So now we're going to test jog mode. We're going to remove control or inhibit on our control box by turning DI00 on. We'll select the jog mode FCB by turning DI01 on, and we're going to then pick our direction using either DI02 or DI03. Of course, you can't jog both directions at once, and we'll select between the speeds with DI04. So we're going to go ahead and do that now, so just hang on a second as I pick up my control box. I'm going to do one other thing which is not in the lab instructions, which will make things a little easier for you watching me do this since I can't show you my control box, my motor, and my screen at once. I'm going to go back to the inputs and outputs screen, and you'll be able to watch when I turn digital inputs on and off by looking at this section here. You'll see these indicators turn on and off. Right now all the switches are off, so they're gray, but when I control them, you can see what I'm flipping. We're going to do that in place of showing you my control box. Okay, so first thing I'm going to do is remove control or inhibit by turning that switch on, DI00. Notice it lit up there. And you can see my motor here, so I'm now ready to jog. I'm going to activate the jog FCB by turning DI01 on. And now I'm going to pick a direction. I'll just go clockwise by turning on DI02. And there we go. We're turning at 100 RPM clockwise. Let's go the other way. I'll shut it off. Turn on DI03. Jogs the other way fine. Let's try the speed. I'm going to turn DI04 on. We should go up to 500 RPM. Looks like high-speed jog is working fine. And now let's just turn all the switches off. Slam. Full stop. Let's go back to the axis circle as we get ready for our next step. What we're going to do now is set up our drive to run with 6 fixed set points. So we're going to move away from jog mode now. We're going to go back and do some configuration of the I/O system. I'll use the shortcut here, inputs and outputs, and I'm going to reconfigure my inputs and outputs according to the instructions. I'm going to set the first one to FCB05, positive direction of rotation, FCB05, negative direction of rotation, FCB05, if you haven't guessed, is speed control, and then I'm going to set the next 3 to the fixed set point bits. Bit 0, bit 1, and bit 2. This will allow me to enter a binary number between 1 and 6 to pick the set points. Now we need to set the set points, so we're going to go to the Set Points menu under Functions and pick Fixed Set Points, this submenu right here. Now I'm going to set this to unipolar fixed set point. Actually, it's already set there. That means it's going to use set points that don't have a sign on them. It's going to pick direction using those two I/O signals. I need to key in my speeds, and I'm going to do that right here. I'm going to just enter my speeds, my 6 speeds, and hit enter after each one. Let me key these in according to the instructions. The first is 150, it's already that. The second is 250. The third is 500. The next one is 750. One after that, 1000. And then finally 1500. So by entering a binary number between 1 and 6, I should be able to pick those speeds. I'm now going to watch what goes on, and I'm going to do this by picking the process values menu right here. And I'm going to pick active drivetrain, and this is going to show me what's happening as I pick these different speeds. And I'm going to be looking right here at rotational speed. So keep your eye there. And I'm going to go ahead now and I'm going to exercise my drive. I'm going to turn on DI00 to remove control or inhibit. I'm going to turn on DI01 or 02 to select direction, and I'm going to enter binary numbers between 001 and 110 to pick my speeds. Let's try it out. All right, let's run through the speeds. I'll remove control or inhibit. I'm going to select positive direction of rotation, and I'm going to turn my first bit on, DI03, which should give us my lowest speed, turning clockwise. All right, next speed. Third speed, works good. Fourth speed, fifth speed, and sixth speed. All right, that works okay. Let's change direction. I'll turn DI01 off and DI02 on. We'll try the same speeds again. Here we go. First speed, second, third, fourth, fifth, and sixth. And everything off. All right, so that is basic set point based terminal control mode. You've got 6 speeds in both directions of rotation, and it takes a total of 5 I/O signals to do that. So that is certainly one way of controlling your VFD without a PLC or anything else, just some switches. Not too bad. Okay, now we're going to change to a slightly different version of terminal control mode. We're just going to make a simple change to the set points and the I/Os. Let's go ahead and take a look at this. We'll go to inputs and outputs first. And I'm going to do something a little weird. I'm going to take away one of these signals. I'm going to change it to no function. And that is because we're switching over to what are called bipolar set points. Those are set points that have a sign to them, and the sign determines direction of rotation. So I really just need anything that calls FCB05 to enable it. It doesn't have to be the positive direction. It could be the negative or one of the other FCB05 calls. I just need to connect one I/O signal to invoke it, and that is it. Now let me go to my set points and make them bipolar. First, I change operating mode to bipolar. Okay, I'm going to go change my set points now to positive negative 250, positive negative 500, and positive negative 1500. So we'll get in here and we'll change this to 250, this to minus 250, that's 500. We'll change this to minus 500. And we'll change this to 1500 and this to minus 1500. And so now we're going to get our direction of rotation from the sign of our set points. Let's go back to process values here so we can actually watch it run. And again, we're going to do a quick test. So I'm going to remove control or inhibit. I'm going to turn on DI01 just to engage the FCB. And by the way, I know the FCB is engaged because the display on the VFD changed to 05, and it also did in MOVI-C. Now I'm going to pick my speeds. I'm going to pick speed 1. Clockwise, speed 2 should be the same speed. Counterclockwise, it is. Speed 3. Clockwise, higher speed. Speed 4. Counterclockwise, higher speed. 5. higher speed clockwise, and speed 6, highest speed counterclockwise. And again, all switches off. All right. I think we can conclude that bipolar set points work as well. Okay, we're now moving on. We're now going to kind of cap off our lab by doing one final reconfiguration. We're going to set up something that could be used for a real application with just your basic MOVI-Drive technology. We're going to reconfigure the axis so we can jog and access some fixed speed set points, and we're going to do it with just the built-in I/O. Doesn't require any expansion. So let's go back and rearrange our I/O a little bit. We'll go back to inputs and outputs again. And we're going to do this. We're going to assign DI01 to jog mode, FCB20. We're going to change DI02 to FCB05. Notice I'm just picking the generic speed control one. That is just fine. And then I'm going to pick jog mode positive and negative. And finally, I'm going to pick my set point bits 0, 1, and 2. Now this doesn't give me full functionality because I don't have enough I/O. Notice I can't access the second jog speed. And the only way I can deal with direction is by using the bipolar mode where I use the positive and negative signs. So there are some limitations to this, but still I managed to make it fit within the 8 standard I/O. All right, let's do one final thing before we wrap up. Maybe we want some status information going back either to some indicator lights, or if we actually wired this up to a controller of some kind that was just interacting with it using binary control, we do need to give it some feedback. So let's configure the digital outputs before we play with this. So we're going to set it up this way. We're going to set D000 to signal output stage enable. That'll just tell us when the drive is running. We're going to then signal as well when our 2 modes are active. So we're going to look for FCB20 jog mode active. That will tell us when we're in jog mode. We're going to set the next one, DI02 to FCB05, speed mode active. That'll let us know which mode we're in. And then we're going to finally set DO03 to fault. That will just tell us if our VFD has faulted on us. And there it is. We won't assign the relay to anything at the moment. Now, you can't see my control box, but you can see on the screen that the fault indicator is lit up green, and you're thinking, is the VFD faulted? And the answer is no, it isn't. Fault is one of those active low signals, which means it goes low or turns off when there's a fault, and it's high when everything is happy. Right now, everything is happy. There's nothing wrong with the VFD, so it's on. And on my control box, that light that corresponds to DO03 is actually lit, but you can't see that, of course. All right, so we're going to now go ahead and just do a quick run through, and I'm going to let you kind of watch my screen to see what switches I'm flipping and what the output lights are doing. So here we go. First, I remove controller inhibit so my drive can operate, and I pick jog mode. So I'm going to activate jog mode by turning DI01 on. And now I'm going to pick a direction. There's a positive jog. There's a negative jog. That works okay. Look at the output status lights. You notice jog mode is activated and also the output stage light is on. All right, so that's good. So jogging clearly works. Let's go to speed control. I'll turn DI02 on. Notice the status indicator shows that FCB05 is active, and so is the output stage. I'm going to pick a speed using DI05. So there's one of my speeds. I'll pick one in the other direction. And I'm not going to test all 6. So there we go. That is essentially a complete terminal control that didn't require any expansion, just the base VFD. This enables you to do something usable. So put this tool in your toolbox and hope you find a use for it someday. And that is the end of session 10. So you have now learned something which can be applied to practical use. There are many real-world applications of terminal control, and perhaps someday you will find one and say that is just the perfect application for terminal control. Let's just use that. In session 11, we will move on to a new topic. We're going to be learning about ramps and stops, something very important in all sorts of VFD operations. See you then.